Hello all. So today let's discuss the problem. Shortest path in directed acyclic graph. Fine. The problem is shortest path in directed acyclic graph. Right. So what happens in this? We are given n, that is the number of nodes. We're given the number of nodes. Let's say n is 6, and we're given the number of edges, that is m, which is 7. And then we're given a matrix H. What is given in this matrix H? The matrix H holds which is the starting node, which is the ending node, and what is the edge weight. Alright. So this contains a list of all these starting nodes as well as ending nodes as well as the edge weight. So let me write down the edge weights which are given for every pair of vertices that we have in this particular question. So it goes something like this. Okay. And what do we need to find? We need to find the shortest path from the source node. Okay. Shortest path from the source node, which is nothing but node 0, to every other node present in this graph. So suppose there are 6 nodes. We need to find the shortest path from node 0 to node 1, 2, 3, 4, 5. Alright. And how do we need to do it? Let's just try to draw the graph and analyze this. So supposingly I have this. So starting node is 0, and then the next node is 1, and the edge weight is 2. So look at this. Then from 0 to 4 I have edge weight as 1. From 4 to 5 I have edge weight as 4. Then from 4 to 2 I have edge weight as, from 4 to 2 I have edge weight as 2. From 1 to 2 I have edge weight as 3. From 2 to 3 I have edge weight as 6. Okay. And from 5 to 3 I have edge weight as 1. Alright. So using this information, how can I find what is the minimum distance? Okay, what is the minimum path that I need to cover? So for node 0, definitely you know that the answer will be 0, right? Because we're initially starting from node 0. Now to get to node 1, we have to like check that is there any path from 0 to 1. So we see yes, there's a path. So we'll print 2, right? We'll print 2 for this. Now for node number 2, which is this one, we see that is there any path to reach node 2? So find that yes, there is a path from here, right? 1, 2. This path is like giving us value of 3, whereas there is another path here also as well, which is giving value of 5. But we think 3 is the minimum path, so we'll take 3. Now for this node number 3, which is the minimum path, I think 1, 4, 1. This gives a path 6, right? For node 4, the minimum path is 1. For node 5, the minimum path is 1 plus 4, 5. And that's it. So that's the answer which we have to return. Now, what do you think is an optimal way? So to solve this problem of shortest path in directed acyclic graph, we can either use Bellman-Ford algorithm or Dijkstra algorithm, right? So let me just try to demonstrate the Bellman-Ford algorithm. What is the code? What is the code for the Bellman-Ford algorithm? Is that we find that for every particular element which we have in this edge, every particular tuple, we know that this is the starting node. So if we write key int u is this edges which is given at edges at I0. Okay. So suppose we traverse for int I equals 0, I less than m, which is number which is n plus plus. Then we find int u is like edges I0. Then v is edges I1, which means it's the second node, and then W is edges at I2. Alright, which means it's this one, right? So we have found out this thing, and now we need to store the distance for every of this, right? Every of the vertex, right? So what we can do previous to this iteration of the loop is that we can declare a vector. Let's say vector int. Okay, let's say vector int distance. Okay, of size n. And let's initialize this with a very large number. Let's say 189. Okay, this is a very large number. It's called like infinity. So we are assigning infinity to every of the node, right, in this distance array. And since we know key from this for the starting node, our answer will always be 0. So let's initialize that with 0 as well. So now what we can do is that we can process all the edges as they come. Okay, so for 0 1 2 you will be holding 0, v will be holding 1, w will be holding 0, and then what we can do is that we can say key distance at v. Alright, because from q we are reaching v, right? Then we can say key it's like distance at v, whatever it's holding previously from this, comma distance of u plus w. So the weight which it, or the cost which it need to travel till distance u, till the node u, and then the weight, we're adding it together, and we're just checking that whichever is min among these two, we're storing it back in v. Alright, so if ever we again find out a minimum path, then we're storing it back in v. Alright, so in this what happens is that we fill this distance array with a proper shortest path, or the proper shortest path which we needed to travel from the root till that point. Alright, now we just need to return this distance array, right? But the condition also said that if any node is not reachable, alright, then we have to return -1 for that node. So for that we just check if distance of I is like 189, that means this node has never been visited. Okay, that means this node has never been visited as v, so it will never be changed. Alright, it will never be changed in this particular function. In that case we need to set the distance of I to -1. Alright, so I think the distance array is pretty much sorted, and we have our answer finally stored in it. The only thing we need to do is return distance from here, right? So this is the entire concept behind the Bellman Ford algorithm. If you see, it's pretty much like comparing two things and then storing the minimum of them. Alright, so I think you had something to learn from this. Thank you.